Okay, so in this video, we want to find the volume of the solid whose base in the xy plane is the region bounded by the curves y equals negative x plus 2 and y equals negative x squared plus 2, and whose cross sections perpendicular to the xy plane are semicircles perpendicular to the y-axis. So let us sketch the region in the xy plane bounded by this line and this downward parabola. But first we need the points of intersection. So let's equate both y values. Send these two terms on the left-hand side, and you obtain x squared minus x is equal to 0. Factor in x. And the solutions now are obviously either x is 0 or x equals 1. If x is 0, take the simpler curve. Negative 0 plus 2 is 2. When x is 1, again take the simpler curve. Negative 1 plus 2, positive 1. So we have our 2 points of intersection. And now we can sketch these two simple curves. So the first curve, of course, is the parabola. Y equals negative x squared plus 2. And the other curve, of course, is a line. Y equals negative x plus 2. And our second point of intersection was the point 1, 1. It's fairly clear from my picture, of course, that this is not up to scale, but that's not important. So we have the region in the first quadrant that corresponds to the base of our solid. And now we're saying that if we take a thin slice of our solid in a way that's perpendicular to the xy plane and now perpendicular to the y-axis, so we're cutting through a thin slice of our solid this way, so the base of our slice will be a thin, now horizontal rectangle. And as we have a thin horizontal slice, the thickness of our slice will be an infinitesimal change along the y-axis, therefore dy, and it will be positioned at an arbitrary y value. And we're saying that if we take a thin slice of our solid this way, the result of the thin slice of the cross-section will be a semicircle. And of course the base of our little semicircle is of course our infinitesimal rectangle. So to find the volume of this little cross-section, of this little semicircle, we need two measurements. First, the radius of our semicircle, and two, the thickness of our semicircle. Well, the thickness is fairly obvious. It is the width of our rectangle, given by dy. And the radius, of course, corresponds to half of the length of the rectangle. So now we need the length of the rectangle. And of course, because we have a dy, everything we measure must be a function of y. So the length of the rectangle is a segment along the x-axis. So we need the larger x value and of course the smaller x value. Well, here we are on the parabola where y is negative x squared plus 2. So let's isolate now for x in terms of y. So first step, send x squared over here, y over there. So x squared equals 2 minus y. And now there are two possible solutions. X is either plus or minus the square root of 2 minus y. But as we are obviously in the first quadrant, x is positive. So x must be the square root of 2 minus y. So we have the x value in terms of y of the right-hand point of the rectangle. And now we need the x value in terms of y of the left-hand point of our rectangle. This will be a little easier. Now we are on the line where y is negative x plus 2. So send x over here, y over there. So x will be 2 minus y. So the length of our rectangle I can put it here, will be of course the larger x value minus the smaller x value. And now we have the length of our rectangle in terms of y, and of course as we've said before, the radius of course is half the length of the rectangle, so the radius is simply this over 2. And now we're good to go. We have the measurements for an arbitrary cross-section of our solid. So let's first find the volume of this little semicircle. Well, the volume will be the area of the semicircle times the thickness. Well, the area of a circle is pi r squared. But since we have only half of a circle, it's pi r squared over 2. So this returns the volume of the face of our semicircle times, of course, the thickness dy returns the volume of our infinitesimal cross-section. We can now obtain from this the total volume by summing up the volume of all the little cross-sections, but now we're summing along the y-axis. So the cross-sections begin here where y equals 1, and they go all the way up to here where y equals 2. So pi over 2. Now if you square this, you get the numerator squared over 4, but 4 times 2 will give you 8, so you get pi over 8. I will leave this all squared. Times, of course, dy. And now we have our definite integral. The simplest way of evaluating this now is to make a u substitution. If you notice, everything in terms of y is a function of 2 minus y. So the choice of u substitution is to let u be 2 minus y. If you make this choice, then du is negative dy. So solving for dy gives you negative du. And we have two y values, y equals 2 and y equals 1. and we need corresponding u values. Well, u is quite simply 2 minus y. So 2 minus 2 is 0. 2 minus 1 is 1. We can factor from this pi over 8 as it is a constant multiple. Integral of, well again, when y was 1, u is also 1. When y is 2, u is 0. This is now just the root of u minus u all squared. And the root can be written as a power of 1/2. And let's not forget that dy is negative of du, and we can bring the negative up front as a constant multiple, and this becomes now a trivial integral. Expand this expression, you'll have powers of u, apply the power rule, then the fundamental theorem of calculus, and you will arrive at a volume of pi over 240. And that's it.